Continuing with these submarine mass movements, the Hawaiian Islands have an interesting problem in that many of the older islands, remember the hotspots under the Big Island, but as you go northwest, the islands become older, and you see dramatic submarine debris flows, including enormous blocks that have slidden off these islands into the deeper water. One of the problems here is obviously this mass movement from a higher elevation to deeper levels in the ocean can cause a water column to move, which can generate tsunamis. I mentioned earlier that I was going to talk about Lake Tahoe, so here we're looking at the California side, Meeks Bay over here, and then on the right over here is the Nevada side. And the bathymetry that was produced about maybe 12, 13 years ago from Lake Tahoe shows a dramatic debris apron of material, blocks that are enormous, that clearly have come from the Meeks Bay area. You can see there could be a scarp. This appears to be a scarp on the western side here at Meeks Bay. Earthquake shaking, there's a number of fault lines that cut across the eastern Sierra here in the Tahoe Basin. Also, there's a little slump that occurred in here. This actually is dated back to about the 1800s. What can cause these mass movements, right? This is a picture of Highway 120 as you're going into Yosemite, and we have a rock slide here that came onto 120 and closed the highway. So what could be causing these? So first of all, we have to set the stage. What's the setting? The rock has to be fractured and weathered. And the fracturing and weathering will eventually lead to soil development, which will lead to that regolith, that softer material that will lie above the bedrock. And usually that regolith is the material that's slumping down here. The other thing is plate tectonics and even erosion, especially glacial erosion, can lead to development of relief. Remember, relief is just an elevation change. So it's a high relief from here to the valley floor down at the bottom over here, right? And then the trigger. We need some sort of trigger to set the mass in motion, and usually those triggers involve earthquakes, right? Some vibration, although they could involve heavy rainfall, which will lead to the saturation of the soil, which leads to loss of friction and loss of cohesion, which can cause material to slump or slide down slope. Now, let's look at fracturing and weathering. So it weakens the substrate. So joints, faulting, they all fracture the rock. The bedrock is covered by that softer regolith, so that's already weaker than the harder bedrock. These materials are much weaker than the intact rock. So if the rock's fractured, if it's a regolith, it's definitely going to be weaker than bedrock. So one example that your book talks about is bedrock. Intact rock here is like granite. It's hard. You're going to step on it, you're not going to really hurt it too hard. Whereas the fractured rock is sort of like a sandcastle. It easily crumbles under weight, right? It's weaker. Now, yeah, so the weaker material will collapse in response to gravitational pull. Now, for intact rock, we're looking at chemical bonds, minerals, cement, holding the grains together for sedimentary rock. So that makes the intact rock stronger, whereas fractured rock, we got only friction between grains holding them together. A little bit of moisture content will lead to electrostatic attraction in terms of surface tension. So hydrogen bonding, that'll help kind of hold. Obviously, if you get more water seeping into the soil, that will expand and you'll lose the friction, lose cohesion, and that can cause a failure to occur. How do we develop this relief, right? Obviously through erosion, but in some cases it could be caused by trying to put a road on an already steep slope. Here we have a slope that already has a pretty steep gradient, and now we want to put a road on this face, and we're going to have to make the slope above actually steeper than it was down below. So oversteeping in the slope can lead to landslides, right? So steeper slopes create a larger force imbalance. So one of the keys to landslides, and engineers who study landslides and slope stability, they worry about the balance between two forces. And the forces they're thinking about is the resistant force, here I'm calling it FR, versus this down slope force, right? Which wants to have the material move down slope. And so whenever the down slope force will exceed the force of resistance, sliding will occur. And usually the way they look at it is that there's going to be some normal force, right? And that's always perpendicular to the slope. And then the downhill force, which is parallel to the slope. And so then we combine those with a pull of gravity. So if we can calculate the pull of gravity, right, draw a vector for it, and then we're going to have lines that go to either the downslope force or the normal force here. So when we have a steeper slope, you see the steeper slope, now the pull of gravity is still vertical, but now note that we have a much longer downhill force than we have a normal resistant force here. So when that happens, when this down slope force exceeds the normal force, we're going to have the tendency for slippage. Other features is we need to develop a plane of weakness, right, or that failure surface. What's happening in those Yosemite rock falls is many of the granitic rocks there formed at depth, right? Remember, the plutonic rocks are forming anywhere from 5 to 10 kilometers deep, right, under quite a bit of pressure. But now we expose those rocks to the surface and we develop these exfoliation or sheeting joints, right? So the sheeting joints are often curved. You develop domes like Sentinel Dome, Half Dome, right? North Dome in Yosemite. And the slope of these exfoliation joints will parallel the slope of the hill here, which can lead to slide blocks. That's what happens with Yosemite. These eventually, the downhill force will exceed the resistant force, and you'll get a slide block that will come down and smash into the valley below. Other failure surfaces include a shale, which is a weaker rock, and otherwise stronger rock like sandstone. And if you weaken that rock by oversaturation, it can lead to a slide block. And note that this slide block, that the strata are parallel to the slope surface. And when that happens, you can get this failure to develop here. Also, we can have metamorphic foliation. If the foliation is parallel to the slope, we can also see a failure surface here. So here's that foliation surface. If we have unconsolidated layers, they can also develop weak bedding planes as well. What are some of the triggers that can set this mass in motion? So I mentioned earthquakes. Vibrations are one of the main ones that can occur. Also, these vibrations will cause the ground, especially loosely consolidated material, to shake like quicksand, where the pore spaces between grains, because here you can have surface tension, hydrogen bonding, kind of hold these things together. But as I shake these apart and make them spread apart, note that I lose that cohesion, right? And the material essentially liquefies, and that's a process called liquefaction, where water pressure between grains causes them to separate and they lose friction. You lose that cohesion and the material just slumps, right? How can we change slopes, right? So, well, maybe if we terrace a slope here, so we have an otherwise gradual slope here, but now we want to put a road here, we make an oversteepened slope here, which can result to failure. If we add buildings, excess irrigation, that can add weight to the regolith here on the surface, which can lead to slumping as well. In fact, one of the Google Earth exercises is asking you to look at this landslide near Jackson Hole, Wyoming. And what's happening here is the strata, the slope of the strata, they're dipping at about the same angle as the slope of this valley. And so a time of heavy precipitation caused a lot of groundwater infiltration to weaken the shale layer here. The shale clay layer developed a slide plane or a failure surface upon which all this material slumped down, right? And so let's look at some of the factors that relate to the strength of the slope, right? So first of all, there's weathering. Weathering makes rock weaker and it transforms it into regolith, right? So both physical and chemical weathering. The amount of vegetation cover. So when you have that regolith slope, that loose soil slope, vegetation tends to strengthen that slope. Roots hold unconsolidated grains. plants absorb excess moisture. And again, water content, right? Surface tension may hold regolith together. That's only if there's a smaller amount of water, the soil moisture. But if you increase that water content, water pressure may push grains apart and you may get that liquefaction, right? Which can lead to slumping. Now, how do we determine areas of risk? Well, if the landslides already happened, it's an area of risk. So we make these landslide maps. In fact, this is for the San Jose area. So here's a little bit of the San Francisco Bay, but we can see kind of the Santa Cruz Mountains over here, the Diablo Range over here. So these red areas indicate areas of landslides, right, where landslide is likely. So areas already had mass wasting. You look for headscarps, tilted trees. You look for piles of loose debris. You look for that hummocky topography, right? So here we have some examples where we have some cracked foundations, some tilted telephone poles. So all these are things that we talked about before, especially with the creep motion. And here are some hummocky ridges over here, right? This last section of the chapter discusses preventing mass movements, and one of the keys, especially for the regolith, is vegetation, because roots can hold unconsolidated material together and anchor, in a sense, the regolith to the bedrock here. One of the keys for preventing landslides is making sure that the drainage is correct, being able to lead water away from the loose material, right? So what we can, in this case, as we lower the water table, we can lower the water table below a weak layer like shale or clay. And other things, we can divert the course of a river a little bit, so we can prevent undercutting of the cliffside here. We can put riprap there at a sea cliff to prevent undercutting of the sea cliffs, and if there's any homes in there, to kind of save those homes as well. We can engineer, they're called crib walls. A crib wall is sort of a engineered feature that'll stabilize a slope. Here they have a retaining wall. Here on Highway 17, they do quite a bit of this cement where they protect the slope here. You could also use bolts to anchor fractured rock here. Here's some bolts.